Good morning. That was a very sweet introduction. Thank you. Can we switch across? Perfect. You'll notice I changed the word limerence because nobody knew what it meant. Limerence, just in case you want to know, is that kind of stage of courtship, where you really fancy somebody else, and you really want them to fancy you. So it's the kind of predatory part of courtship. So it's like infatuation, but more dangerous. So anyway. So I don't know about you. I go to a fair number of conferences. I think this conference has had the highest percentage of really killer talks of any conference I've been to I can remember. So I just want to... just thank you guys. It's been a blast. So I'll come back if I'm invited. All right, so let's see if we can get this to work. Yay. Why do I want to talk about this? Well, there's a couple of reasons. Firstly, the languages we use are our tools. And, obviously that used to say, tools maketh the man, but you can't say that anymore. So I had tools maketh the person, but then that kind of excluded babonos and certain covids like crows and octopus. And I couldn't remember if octopus was cephalopods or not, so I just changed it to user. But tools affect what you do. Thoreau said, we become tools of our tools, which is a little bit scary. And the language we use is actually the language, it actually affects us. It affects us a lot. There's another reason I wanted to do this. Recently, I've been kind of getting unhappy with the state of the way I think about programming. That's a weird thing to say. I am moving away from object-oriented programming because I think we're using it wrong. But I'm not 100% sure I know why I think we're using it wrong. So I was sitting there trying to analyze, why do I have this feeling, right? What is it that makes me think this? And I realized that it's actually an accumulation of all of the languages that I've been using and things that they have told me as I was developing as a developer. So as kind of an indulgence to me, I thought I'd like to go through and actually have a look at some of those languages and explain why they make a difference to me. I'm not trying to sell you on languages. I'm not trying to sell you on my point of view, right? This is purely me being like selfish and just talking about me for a while. However, I do think there's a message here, and we'll get to that a bit later on. The other reason I want to do this is I really want to say thank you. Thank you to an environment which has let me play for so long. So without any ado, I have a list here of just a sampling of languages and the impact that they had on me. Let's go back. So we're going to go back in time. Oh, whoa, don't stand close to that and look at it. Ooh. We're going to go back in time to 1972. Matter of interest, how many people were born in before? 1, 2, 3, 4, 5. Excellent. Okay. That makes me feel young. 1972, I was in secondary school in England, and it was the end of the summer term, and they'd run out of content for me. So they sent me across the road to the local technical college, who were just experimenting with a course on programming. So I had nothing else to do, so I went across the road. I was going to be a mathematician, and that was pretty set. I was doing all math A-levels and this kind of stuff. I went across the road and sat in this little hut and started programming. Now let me just give you a bit of history here, tell you how I started programming. I started using BASIC, which, as you all know, stands for Beginner's All-Purpose Symbolic Instruction Code. Whoa, I know. And we were coding in an incredibly sophisticated IDE, which was an ASR33 teletype. It was offline because it was expensive to be dialed into a computer. So you would prepare your programs by punching them onto paper tape. And you would do that offline and type, 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 type. Once you were ready, you picked up a telephone and you dialed the computer's modem, and then you took the handset and stuck it into that thing over there, which is called an acoustic coupler. That's a modem. And the two computers would whistle back and forth at each other until they were talking. You would then take the paper tape and you would feed it into the reader on the ASR33, and that would then send your program up to the mainframe, which in this case was an ICL 1904A. And it would look at your program, laugh, and send back all the error messages. Just for your edification, we were starting off using 110 baud, 110 bits per second. So, little quiz to get you warmed up. You're using a 110 baud connection, and you want to transfer a gigabyte. How long is it going to take you? Okay, show of hands, how many people think it's going to take maybe about a day? 5 days. 2, no, let's not do, a month. 1 year. $105 days. So, you know, you're in the right order of magnitude there. Yeah, it was not the speediest way of developing code. It is not really the environment expect to fall in love. But as everybody does in BASIC, this is the equivalent of hello world, it's hello me, and I fell in love. And I totally changed what I was going to do for the rest of my life. And I still don't know quite why, but I think it's because I found a way of expressing myself. I found a way of making my thoughts more concrete. I'm not an artist, I can't draw, I can't play an instrument. So this was actually, for me, a really enabling technology. So it is fair to say that the BASIC programming language is the most influential language in my life because it changed my life. Did I use it going forward? Hell no. I went to college. Once I discovered this, I looked around. There weren't many places in the UK at the time offering computer science, but Imperial College had just started a course the previous year. So I went along and joined that. It was incredible because these people had no idea what they were doing. It was like I said, I was in the second cohort to go through, and they didn't know how to teach computer science, and that was great because they experimented on this. They tried all sorts of things. And so we got to play with all sorts of things. Our primary programming language was Pascal, but we tried probably, I would guess we probably did over a dozen different languages during those 3 years. One of the most significant ones for me was a language called Simula. Simula 67. The 67 actually means 1967, which is when the first version was produced. Simula, in many ways, would be considered an advanced language today. It's widely held to be the first OO language, but that wasn't really its purpose. But it was just kind of incidental. Simula was designed to help people write discrete event simulations. That's when you have entities that have to move through a system and they queue for resources and then move on to the next resource and the next one and the next one. And they had a problem. They needed to be able to get data and code like lumped together. And so they said, well, what should we do? I know, we'll invent an entire new paradigm of programming, object orientation. And so this is a Simula program. Hello. Oh, there we go. So that's a base class. You'll notice it actually says class, animal. It's got a slightly funky syntax for the virtual procedure there because you can rename procedures as you make them virtual, but that's a virtual procedure, which means this is a base class. You can't instantiate it directly. Here is a subclass. Notice that they do something which we don't do, and this is better. They prefix it with the name of the parent class, not suffix it. Because when you think about it, that's like a type declaration, right? Our class cat is of type animal. It makes a lot more sense that way around. Anyway, and we implement the virtual function in there, and then we do the same thing down here for dog. If we want to run that code, this is a bit funky. And pets is an array indexed from 1 to 3 of references to an animal. So Simula, you explicitly say whether something's a reference or not. And then the somewhat phallic operator in the middle there is the assign a reference operator. So we create 3 objects. Notice we're using new, right? Add a couple of parentheses. This could be any language you use today. From Ruby, where it would be .new. And then we just iterate through it and make our pets speak, and out it comes. Simula, that's really irrelevant to Simula. It is such a profoundly deep language. It has so many things that we cannot do today built into it. You can choose how your object construction goes. You can basically wrap constructors in all sorts of weird ways, which is incredible. Classes, the implementation of classes is fantastic. A class is a closure over its instance methods. And that's how they share instance variables. Really elegant, really, really elegant. It's got coroutining built in, which is really nice. Type inspection, compile time, and runtime. And it's got a very interesting, well, it's not just inheritance, it's how initialization takes place. It's a very interesting language. So for me, Simula opened my eyes. Excuse me. It opened my eyes to a totally different way of thinking about programming. Up until then, I've been doing procedural programming in Pascal and Fortran and all those kind of languages. And now suddenly I came across a brand new way of organizing my thoughts. The idea of having state that is local inside an object. The idea of the state and the actions being tied together. I mean, that's really cool. The fact you can actually explicitly make your abstraction and create hierarchies of abstraction was really neat. And then lastly, because it is a simulation language, it's actually event loop driven. Just like, say, JavaScript is. So this language was way ahead of its time, and it really profoundly changed me and the way I program going forward. And even then, when I was writing more procedural languages, I would tend to do it with one eye on Simula and the way Simula would do things. So one of my goals here is to use languages, or to come up with at least 1 or 2 languages that Mats hasn't heard of. So, have you heard of apt? Yay! Success! I can go home. All right. Apt was said. They tried all sorts of experiments on us. One of them was, they had a professor whose specialty was machine tooling. And we went and we did a semester learning how to program big CNC machines, the ones that cut out large chunks of metal. And back then they were programmed using paper tape, and there was like a low-level set of instructions on paper tape. There was a compiler that would produce those low-level instructions. One of those compilers was called apt. I have no idea what it stands for. So let's imagine we wanted to cut out that piece. What we would start by doing is we'd write an apt program, and we'd start off by defining a geometry. So we would say, okay, let's have a point called P1 at 50, 50, and another point called P2 at minus 50, minus 50. So far, so good. This is where it gets fun. L1 is a line that passes through P1 parallel to the y-axis. L2 is a line that goes through P2 perpendicular to L1. Is that getting cool? Line 3 is the same kind of thing, parallel to line 1, and then line 4 again is perpendicular to line 1. So we define all our geometry in terms of other things. We create two circles, and they are bounded by L1, L2, and L2, L3, L4. Remember, we're doing CNC, so we have a z-axis as well, z-axis. And we're defining two planes, one of which is of the material, and the other which is the embedded into the material plane. And then, the scary part is we actually tell the machine to move. So we tell the machine to load up tool 1 with cutter number 20. The spindle speed is 3,000 RPM, clockwise direction, please. And we're going to go to the start point, and we are at 70, and rapidly we're going to go to L1, and then down to plane 2. So we come across the surface, then dig down into plane 2. So at that point, we have our little cutter head there. It comes to here, and now it's going to follow these instructions and cut out our shape. And it handles all of the geometry required to make sure that what I've defined here is the outer side of the thing, and so it makes it move in the appropriate places. And that's really cool. Really, really cool. apt was first created in 1956. And it is actually still used today, which is incredible. I suspect it looks a little bit different. For me, apt was, again, an eye-opener. First of all, it was the first genuinely domain-specific language I used. You could argue that Simular was kind of a domain-specific language for simulation, but apt really was. You know, I'm a machine tool, and that's what I'm going to be able to do. It was also the first time I had used constraint-based programming. This idea of, here's a line that goes through this point perpendicular to this thing. That was really cool, because suddenly I realized I didn't actually have to tell the computer how to do something, but instead I could tell it what I wanted to happen. And that was, wow, that's cool. And most cool of all, I got to play with a massive, big, scary industrial milling machine, which spray a lot of oil, I can tell you. All right, so that was my college days, mostly. I started a PhD program and I gave it up because, to be honest with you, I wasn't convinced I was having fun. And I went and joined a, nowadays you call it a startup. Back then it was a sweatshop. And the first projects we took were mostly on PDP-11s. That is what a PDP-11 processor, an 1170, looks like. It's a classic computer. It's got switches that toggle up and down and lights that flash, and it's just cool. Even cooler is the fact I've got that in my office. It's not actually a PDP-11. It's actually a 2/3 size recreation of a PDP-11, and it works. It actually has all the little toggle switches work, all the little LEDs work. It even has a key lock on it, so you can stop people playing with it. Inside it is a Raspberry Pi that runs a PDP-1170 emulator, including everything, the I/O, the memory management, everything else. Ironically, they had to slow it down because it ran too fast. But anyway, that's a PDP-11. It is a 16-bit computer with an 8-bit byte, and you have to say that because not all computers were 8-bit bytes back then. It had 64K of directly accessible memory, of which 56K was usable. 8 registers, 2 of them had special purpose, the rest were for you. Memory mapped I/O, so there were no I/O instructions. You did I/O by writing to certain registers in memory. And it was probably the most popular microcomputer of the 70s. And to my mind, it has the most elegant architecture of any machine ever produced. I could do an entire day on the PDP-11, but I'm not going to, don't worry. One of the things that is stunning about the PDP-11 is you're writing in assembler. You're telling it individual machine instructions what to do. And yet the code you write can be as compact as it would have been in C or any other language. So here's a function or a subroutine that decides whether or not a string is a palindrome. We start off, we have the registers, right, are just things we can use for scratch values. They can point to memory, they can have values in them. So on entry, register 0 points to the string that we want to find out if it's a palindrome. That first little chunk of 3 lines there finds the end of the string. And at the end of it, R1 is pointing 1 character past the end of the string. So now what we're going to do is we're going to go through the string, looking at successive characters, 1 at the start, 1 at the end. If they're the same, we're going to add 1 to the start, subtract 1 from the end, and do the comparison again until our pointers meet. And if they meet, then it's a palindrome. But the amazing thing is that little instruction there. CMPB, compare byte. Most instructions that reference values in the PDP-11 can reference them in 7 different ways, including I want the value in that register. I want the value at the memory location pointed to by that register. What this guy's doing is saying, to find my first operand, go to the byte pointed to by R0, load it into the operand, and now increment R0. Now, next one. I'm going to go and look in the memory referenced by R1, but before I do it, I want to decrement R1. So I'm going to pre-decrement it, then go fetch it. So I've now loaded the 2 bytes and moved those registers toward each other, 1 byte at each end. And I did that in 1 instruction. If they are not equal, then it's not a palindrome and we exit. Otherwise, if the pointers have met, then we're done, and it is a palindrome, or we just try again. Just to show you how influential PDP-11 was, if you're a C programmer, you'll recognize something like this, right? And if we ignore the kind of namby-pamby, sort of wussy version of C called C++ and go back to the real C, right? Tell me, hello, what is hello there? Somebody knows. I know Mats knows, because he's a C programmer. It's a pointer to the first character of what? Yeah, it's in memory. It's a string, and it's just a sequence of characters. But in C, the convention is a string ends with a null byte, with a byte of zeros. And that way you don't have to encode the length in a string. I don't know, but I have a theory that that's because of the PDP-11, which was very big at Bell Labs at the time. So the code that equivalent to this is I'm going to move the location of the buffer into R0, the location of greet into R1, and call string copy. Okay, so far so good. String copy in PDP-11 assembler is effectively 2 instructions. We just move a byte referenced by well, that should be R0 and R1, sorry. But move a byte from there to there, increment both registers. If the byte we moved was 0, stop. Otherwise, go around and do it again. Like I say, it is incredibly elegant. But on top of that, it was such an education. Because when they arrive, you have to plug things into them. You have to plug the peripherals in. You have to wire wrap connectors to configure things. You get very familiar and very comfortable messing around with hardware and diagnosing hardware problems. And the fact that you're writing an assembler means that you really have to understand the code that you're doing. So I actually was forced to think really hard about the algorithms I was using and how to make them work efficiently in a very limited environment. And as a result of that, you actually get pretty good at performance and anticipating what performance is going to be like. Okay. Next. And remember, these are just languages that kind of like maybe go, ooh. Prolog. How many people have played with Prolog? Oh my word, fantastic. Was that at school or was that in your job? At school, yeah, okay. So Prolog is a really weird language in that it is really, really cool and nobody really uses it. Prolog is designed to explore logical programs. So one of the things it has is facts. And a fact is simply an assertion. The names are totally irrelevant, they're just symbols. So I'm saying that Paris is a city and Rome is a city. And I can have multiple atoms, they're called, in one of these assertions. So I can say the capital of France is Paris. Then you can make queries on those. So I can say, is Rome a city? And what you're actually doing is challenging Prolog effectively to find the opposite of that. If it can prove that that's not true, then it can say no. Otherwise it says, yes, probably true. Now in this case, yeah, it's a known fact. Rome is a city. But I can take it further. I can use variables. Is X a city? So Prolog says, well, I'm going to have to work out what values I can give X to make this true. And it'll say, oh, if X is Paris, then yeah, this is true. But it doesn't stop there. And it says also, oh, by the way, if X is Rome, then it's also true. I don't have to supply all or no parameters. So here I can say the capital of BAH is C, which is a variable. So it's going to have to go and search, and it will find that Sarajevo satisfies that condition. I can do it the other way around, right? What country has Sarajevo as a capital? And it tells me. Or I can just go hog wild and say, are there X's and Y's such that X has a capital Y? And it will report all of them. So on its own, that's kind of cool but useless. But then you take it a step further and you add rules. And a rule looks like this. So this is effectively, well, no, it's a rule. So part one of this rule says that A is bigger than B, so bigger than is my rule, if A is bigger than B. That's this one over here. So if it's immediately bigger than, then it's bigger than. And then we do have a recursive step that says A is bigger than B if A is bigger than some other value C, and C is bigger than B. And it goes through and it works it all out. Now, if you are an Erlang programmer, this is going to look really familiar, the syntax, right? We call these things atoms. We have full stops at the end of clauses. This thing in Prolog is called a reduction, because we're basically taking facts and reducing them down a bit. All of these things made their way into Erlang, because Joe Armstrong, bless him, was a really big fan of Prolog. And in fact, the first version of Erlang was actually parallel Prolog. So he was attempting to program telephone exchanges using Prolog. And they gave up, I believe, because it turned out to be slow and unpredictable. But I may be wrong about that. So again, it's all about me. Prolog and me, again, was eye-opening. It was just so much fun to work out how I could express stuff where I didn't actually have to tell the computer how to do the work. I just have to set up a whole bunch of relationships and let it do it for me. Is it efficient? Hell no. Right? Depending on like the order in which you write some of the rules, it can take a second or it can take the lifetime of the universe to run the program. But that's part of the joy. It also got me really comfortable with backtracking, because obviously that's how it's doing what it's doing. It's searching that space of facts. And if it finds a contradiction, it has to go back up and try and search again. So Prolog was a big language for me. Everyone's going to grow in the next one. SQL. I possibly am the only human being on the planet who loves SQL. Oh, I have a fellow deviant there. Oh, 2, 3, okay. Let's all form a club. Yeah, look at that, you know, SQL Anonymous or something. I think SQL is just gorgeous. And to do this talk, I was just thinking, okay, so how can I illustrate some really, really stupid SQL? And at the time, I was looking at the pragmatic bookshelf royalty system. And we have a part of the schema looks a bit like this. So the SKUs are the things we sell, like a PDF of a book or a paper book, whatever else. We have a table that says for any particular order how much royalty they get off that SKU. We have for every particular SKU some fixed costs. So like copy edit or printing or whatever else is a fixed cost. And then we have income. And as income arrives, it's kind of accumulated over here. And then once a month, we run actually a fairly small amount of code that goes through and for all of the new income, assigns it to particular people. That's the royalty payments. And that is currently maybe 100, 150 lines of Ruby. And I thought, okay, what would happen if I tried to do it pure SQL? And it turns out it's not too hard. It's not the prettiest SQL in the world, but you can actually do the entire calculation and get the correct result just using SQL. Admittedly, there are 3 levels of nested query, but surprisingly, it actually doesn't run slowly. I love that. To me, it's just so cool. Thinking in sets and in terms of set operations is just kind of like a new way of looking at it. So I would actually call SQL is a DSL for set manipulation. And I really love DSLs. It is declarative 90% of the time, 99% of the time according to the slide. So I don't have to be telling it how to do something. I tell it what I want done. I describe to it the conditions that will make me happy. and then bless it, it goes away and tries to make me happy. And who could want more? The other thing I love about SQL is people constantly come and say, so how much money did we make off ebooks that went through channel 27 in the month of May and June, right? And I don't have the time to write like a nice GUI for that, so I just slap a little bit of SQL in, and out comes the answer. So it's nice that way. I've been using SQL now for, I don't know, 30 years or so, and we're still friends. All right, one more. Mats, wake up. Pick. Do you know Pick? He knows Pick. Damn. All right, Pick came about from Bell Labs, as so many good things did, as part of their Documenters Workbench. When they first developed Unix, they needed a way to describe APIs and stuff. You know that now as the man system. You can type man followed by something, and it gives you information about that thing. Well, the source that is used to describe that is a format called nroff. And if you have a look at it, it's got like commands that start with a dot and then text and everything else. But the cool thing about nroff is, like everything else in Unix, you can pipe things into it. And so you can have a whole bunch of preprocessors, which are separate programs, and you feed your original source in one end, and it goes through and it does all of the preprocessing, and in the end you feed it into nroff and you get the pictures, or troff now. So Pick is one of these preprocessors. It draws pictures. So a basic picture could look like this. Box with label import, an arrow, box label process, an arrow, box labeled output. All right, you say Mermaid can do that. Sure it can, but it couldn't do it in 1974. We can make it a little bit more complicated. A box right called the event stream, a box with a corner radius of 0.1, finite state machine, an arrow, new state. And then this is where it gets fun. A line with an arrow at both ends, down from the last box, which is that second line there. So we've now drawn the arrow down, and it now knows we're going down direction. Box same actions means the same parameters as the last box you drew. So it's got the same border radius as that one. We can take it a little bit further. I'll draw a spline. It's going to be a dashed line, and we'll get to chop in a second. I want to go from the last arrow, which normally by default means the center, but I'm going to go from the center of the arrow up 0.7, across to the center of the other arrow, but still up 0.7, and then down to the arrow. And then when I say chop, it actually cuts the start and end of the line short, so I don't overwrite the text. And I can put colors and everything else into it as well. It's a really sweet little tool for drawing pictures. Or it's a horrendous tool for drawing pictures. Nowadays, you'd probably do that in, I don't know what. But one of the nice things about this is it's a plain text format. So making changes to it, global changes, is really easy. And because it's part of a pipeline, you can pre-process stuff to generate pick and then generate your output. And we did that a lot. Back when I had my own company, I was doing documentation for clients. We had a set of standard pick macros. You can see you could actually define macros in it. And we used those for drawing all sorts of diagrams. And we just had a preprocessor that then generated pick, and then it went into trough. One of my favorite things with pick is I can draw a line between those two boxes, and then I can put a circle at 1/4 of the way between the start and the end. And then I could have said a half, but I just like the symmetry of 2/4, and then 3/4. And that's kind of pragmatic. That's the kind of thing you actually want to do when you're drawing pictures. So it's really nice. And of course, you can go crazy. This is a little bit of pick that just draws circles. All right. So yet another DSL. Okay, look at the circle. Look at the circle. Buy more books. Buy more books. All right. It's another DSL, and it's another constraint-based language. You may have noticed a pattern here. If I can get the computer to do the work for me, I'm really happy. So it's constraint-based. It integrates via pipelines as opposed to APIs, which makes it infinitely more flexible to use. It's a really good example of do what I mean. Because 90% of the time you can say, draw a line from the first box to the third box and put a dot halfway between them, and it just works. And I actually still use it. Not as much as I used to, but I still use it on occasion. I'm getting towards the end, don't worry. XSLT. Oh, I have some fans. Yay, okay. XSLT, I came into through necessity. So at the Pragmatic Bookshelf, we write our books nowadays in Markdown. In the old days, it was in a markup language called PML. And it might, literally a book, it'd be like a hash chapter 1 at the top, but apart from that, a book could look like that. It wouldn't sell very many, but we then, we give all of our authors the toolchain. So if they want to, they can actually build all of their books locally. The only requirement is you have Java installed, because all of our tools are written in Ruby, and they all run under JRuby. So if you have Java installed, it just runs. So we start off with a pipeline. Just like Trough, right? We have independent processes that are just pre-processing all of our data. There's about a dozen of them in our toolchain that do various things to manipulate. And it runs in parallel, which is kind of cool. And the result is it produces an XML file. And the XML file kind of looks a little bit like HTML, but it's got some special stuff that we need. And then I had the problem. I needed to take that file and generate a nice looking PDF from it. And the technology used to create PDFs from XML is called FO, formatting objects. Formatting objects are ugly, ugly as sin. Nobody wants to be writing those by hand. So I needed a technology that will translate one to the other. And that's where XSLT comes in. XSLT is a transformation language, fundamentally for XML, but it'll work with plain text and stuff as well. So I can take this, feed it through our XSLT processor, it produces that, and then I feed that through something called an FO, a formatting object processor, and I actually end up with a book. And it's actually pretty easy. If you look at our input and output here, let's just take a small part here, that enter. That has to become FO colon inline, font style equals italic, enter, FO inline. And to achieve that in XSLT, you write a pattern match. They call it a template, but really it's a pattern match. And a pattern match looks like this. A template, it's matching. That is effectively a CSS selector. So that's matching an env tag. Whenever it finds an env tag, it's now going to do whatever's in the body here. If it doesn't start XSL colon, it just outputs it to the stream. So we output FO inline font style equals italic, and now we call ourselves recursively. We call the entire matcher recursively. So if it was allowed by the syntax, I could have an entire book in that env tag, and it would work. And basically, the thing that generates our printed books from our XML files is a couple of thousand lines of XSLT. And it turns out to be really nice to maintain. It's a really easy way to make changes. So XSLT It's a functional language. It's immutable. It works purely by transforming things in a functional way. It's also a DSL. Yay! It operates through the recursive application of transformations. And as we'll see in a minute, that's a big deal. It is ugly, but it's powerful. And to be honest with you, I can live with ugly if it does what I need. Interestingly, it's also built into every browser you've got. So should you ever find yourself, and it works with HTML, so should you ever find yourself needing to do some weird transformation on HTML is being sent down from the server, you can actually do it in browser very, very simply using XSLT. And I think XSLT was probably, for me, the thing that most completed my kind of transformation from an OO programmer into a transform things programmer. But we're talking about languages that really influence me. And there are a few more. You may have heard of this one. I'm not going to tell you all about the features of Ruby because you probably know more than I do about them. So I'm going to go straight to the Ruby and me slide. I think the first major thing about Ruby is it works the way I think. Or possibly, Ruby has trained me to think the way I should to use Ruby. I'm not too sure which, but I don't care. And Ruby makes me feel good when I get work done. And that's nice, because I have to get the work done. And I've been using Ruby now since 1998, which I think, was that 0.6? I can't remember. 0.4, you're right, 0.4. And you know what? I actually have some original code there, and it still runs. Which is, I can't think of another environment with the exception maybe of C, where that would be true. And that's 100% down to this gentleman. Now, am I right? All right. Now, so Ruby is my love, I guess. Ruby is the language I keep coming back to. That doesn't mean I don't every now and then go out and have affairs. So I like Elixir a lot. Elixir has some things which I think are incredibly elegant. It has pipelines. So it takes the value on the left-hand side of the pipeline and feeds it into the function on the right-hand side as the first parameter. That's very nice. It means I can express transformations. Remember, I like transformations. It has macros. In fact, in Elixir, almost all of the built-in control structures don't actually exist in the syntax. If statements and things like that are not syntactic elements. They're actually function calls using macros. And that means that the case statement here, normally you would write case, some expression, do, and then your matches. But if I put it in a pipeline, then the first parameter, which is the expression, gets passed in from the previous operation. So it just integrates beautifully into my pipeline like that. And it runs on the beam, which means I get a whole bunch of decent performance, high uptime code that runs in a distributed environment. So for me, Elixir showed me eye-opening macros and the power of immutability and pipelines. So I talk about love. Each of these languages, as it says, has at some point captivated me and has changed the way I think. I've adapted to them, and every now and then they've adapted to me. And I also have this thing where I will have temporary infatuations. In fact, I'm encouraging myself to have that. I go out and I try and look for languages and just play with them and see what I think. If I'm still interested at the end of the day, I'll play a bit more. Otherwise, I'll just move on. That's how I found Ruby. Ruby was a download on a Usenet group, Ask Your Parents, which it came, I think it's like 15 separate parts that you had to combine together and then untar and then build. And I did that, and I pretty much, it was a bit like BASIC actually. The first time I redefined plus, I went, this is my language. Just really quickly, my current infatuation is a language called Unison. Unison is a purely functional language. It has strict typing, immutable code. Immutable code, I'll come back to that in a second. Its state is managed. In many languages, you use monads to handle this. In Unison, you have abilities, which other languages called effects or algebraic effects. In Unison, adding something like distributed code or distributing an algorithm is simply a question of adding an effect to it, and it's all handled for you. So here's a little simple bit of Unison code. It doubles a number. And remember I talked about immutable code? When you write source files like this in Unison, Unison calls them scratch files because you delete them after you've finished. Instead, what happens is you take the code, Unison is going to compile it, and at some point in that process produce effectively an AST. Now, the AST is a data structure. Here's the thing, you can take a data structure and find a hash, which it does. And then it says, double is the code that corresponds to that hash. All right? Now, we take this code and we store it up in the cloud. And it's content addressable. It's accessed by hash. And our program still thinks of it in terms of double, and we have a mapping from double to that hash. So whenever I call double, I get that code. But here's the thing. If someone comes along and changes double and makes it multiply by 3, it'll have a different hash. So I will still use that version of it. So there's no dependency checking. There's no build tool required. It just finds the right version because that's all there is. If somebody else writes a function called times2, it uses different variable names, different function name, but guess what? It's got the same hash, and so in the cloud, it's the same function. And in fact, you can even search for functions by giving it the signature that you want, and it will come back and tell you, oh, someone's already written that. I talked about abilities. Well, an ability in Unison is basically an annotation which causes it to wrap code in a kind of stateful wrapper. So all I need to do to make this MapReduce distributed is add remote as an ability to that line. I mean, honestly, it's a bit more complicated than that, but not in practice. Am I using Unison in production? Hell no. But it's a blast to think about what you can do with it. For me, it's had the highest density of new ideas of anything I've seen for a long time. And if you've only got limited time, I would strongly recommend Unison as being where you spend it. I think Unison gives us some ideas about the future of programming. And I'll talk about that in just a second. Oh, actually, I'll talk about it now. What is the future of programming? I'm glad you asked. I have been wanting to use the shimmer effect ever since I started using Keynote. In fact, you know what? Okay, I don't know, but I have a theory. I have a feeling. How many minutes? 2. Okay. I've got 107 more slides. All right. I think the future, we're not going to program the way we program now. I think the future is going to be producing clouds of functions. Think about the Unison model and throwing functions into the cloud. These functions will be invoked by pattern matching. In that way, if you've ever looked at blackboard systems like Linda, it's going to be similar to that. Our code is going to execute because it's the thing it does when it sees this particular pattern of data come in. Take that data and throw it back out into this big pool of data. And then some other function is going to go, oh, I can handle that. And eventually it will all get done. State is obviously going to evolve in this system. And it's going to evolve in maybe unpredictable ways. But that state change creates pattern matching, which keeps the process going. And we evolve it by evolving immutable code. So the existing code we've written is still going to be there. It's still going to be referenced by people that wanted to use it, but I can change it in the future, and it will just pick it up the next time it has to get run. So this is my journey. I cannot emphasize enough how much I have benefited from the work of others. Right? My entire career has been built on the shoulders of people way smarter and probably way more dedicated than I am. And I am profoundly, profoundly grateful to all of those people. I've tried to give back when I can, but my contribution is nowhere close to what they have done. Each of the languages I've talked about has changed the way I think. They have changed me as a person. And each of them has brought me some kind of joy. And that's why I keep doing what I'm doing. And some of them, like Ruby, like Basic, have actually changed my life totally. It's gone in a totally different direction to the way I was expecting. So that's my journey. The whole point of this entire thing is this slide. What's your journey? Are you kind of, I'm a Ruby programmer, and that's what I do? Or are you prepared to take the occasional risk and explore other things? It doesn't mean you're turning your back on your first love. It's just bringing a bit of spice to the arrangement. Yeah? Are you prepared to look backwards? Most of the things I talked about here are at least 40 years old. They implemented these things on machines that, I mean, you can't get computers that small nowadays, right? There's no comparison. Right? The average cell phone probably has more computing power than the entire planet had in 1970. Right? It's just not comparable. And they managed to achieve incredible things because they didn't have boundaries. They didn't know how it was supposed to be. So they just went out there and made it up. And 90% of it was crap, but some of it was so, so good. Are you playing with the future? I have a rule of 3. If some technology comes across my screen 3 times over the space of 2 weeks, I put it on a list and then I go and play with it. And that's how I found Ruby. That's how I found almost everything I use. If you don't do that, then there's a word for what you'll become. Maintenance programmer. Don't do that. And then last thing, are you having fun? What you do is really hard. What you do involves taking risks. It's not easy. So, you deserve to have fun. Are you having fun? If not, make it fun. Thank you.